Students, in this video we are going to find what is the magnetic field along the axial and along the equatorial point of a bar magnet. So, before going into derivation, we have to study two new terms. First one is magnetic dipole. Now, magnetic dipole means equal and opposite poles separated by a distance is what we call a magnetic dipole. And a very common example for magnetic dipole is bar magnet. A bar magnet is a very good example for a magnetic dipole. A current carrying loop is also an example for magnetic dipole. Now, next term is magnetic dipole moment. Magnetic dipole moment is actually the product of pole strength and magnetic length. And it is denoted by the letter, small letter m. So small letter m is equal to magnetic pole strength into magnetic length 2L. And m is a vector quantity and the direction of m, that is direction of magnetic dipole moment, is from south pole to north pole. So, m is a vector quantity and its direction is from south pole of the magnet to the north pole, and the unit of m is ampere meter square or joule Tesla raised to -1. Now, let us see what is the magnetic field at point P along the axial or axial point of a bar magnet. Imagine you have a bar magnet and the distance between the poles is what we call the magnetic length 2L. If O is the center of a bar magnet, then distance from O to south pole and to north pole will be L. Now, I wish to find out what is the magnetic field at point P along the axis of the magnet, and point P is at a distance R from the center of the magnet. Therefore, distance between north pole and P will be actually what? R minus L, and distance between south pole and point P will be R plus L. Now, my aim is to find what? The magnetic field at point P. Now, we know that field at a particular point is actually what? It is the force experienced by a unit north pole placed at that particular point. So, first I am going to find out what is the effect or what is the direction of force at point P due to north pole and south pole of my bar magnet. For that I am going to keep a unit north pole here, and I am going to find out what is the direction of force acting at the unit north pole due to south pole and north pole of my bar magnet. First, let us consider the case of north pole and unit north pole. You know, like poles repel each other. So, definitely north pole will repel the unit north pole. So, direction will be pointing outward. Whereas, unlike poles, they attract each other. So, unit north pole will attract the south pole. So, direction will be towards the south pole. S. So, resultant field at point P will be the net effect of Fn and Fs. Now, according to Coulomb's law of magnetism, force of attraction or repulsion between two poles is given by F is equal to mu 0 by 4 pi Qm1 Qm2 divided by R square. This is the general equation. Now, in our case, our second pole is unit north pole. So, Qm2 is equal to what? 1 ampere meter. Therefore, force acting at point P due to north pole of the magnet is equal to what? Is equal to mu 0 by 4 pi qm divided by, now what is the distance between north pole and point P? It is r minus L. So divided by r minus L the whole square. And what is the direction? Direction is from north pole to point P. So we can write direction is along NP. Now, next, force acting at point P due to south pole of a magnet. We'll name this as Fn and this as Fs is equal to mu 0 by 4 pi qm divided by, what is the distance? R plus L. So r plus L the whole square. Now what is the direction? Now direction is from P to S. So we can write along PS. Therefore, the net force acting at point P will be equal to, we'll name it as F net force at point P. F is equal to what? Now, if this is point P, Fn is acting in this direction and Fs is acting in this direction. So, resultant force will be the difference of these two forces. So, F is equal to Fn minus Fs, and this is equal to what? It is equal to the magnetic field at that point. So, we can call it as B axial. Therefore, B axial is equal to what? Fn minus Fs. I am going to substitute the value of Fn and Fs. We will get mu 0 by 4 pi, which is common to both Fn and Fs. I am taking it outside. Qm is also common. So that is outside the bracket. Remaining we get 1 by r minus L the whole square minus 1 by r plus L the whole square. Now we know that A minus B into A plus B is what? A square minus B square. So this denominator term will become equal to mu 0 by 4 pi qm into, we get 4 RL divided by r square minus L square the whole square. Now, so we get, I'm going to write the equation once more. B axial is equal to mu 0 by 4 pi 4 qm L divided by RL divided by r square minus L square the whole square. Now we know that 2 qm into 2L is what? Magnetic dipole moment m. So I am going to split this 4 into 2 parts, 2 into 2. And I am going to rearrange the equation. So we get B axial is equal to mu 0 by 4 pi into qm into 2L into 2r divided by r square minus L square the whole square, which is equal to mu 0 by 4 pi qm into 2L is what? M. So m into 2r, so 2mr divided by r square minus L square the whole square. This is the equation for magnetic field intensity at at the axial point of a bar magnet. Now imagine my point P is very far away, that is compared to the length of the magnet, R is very much greater, or length of the magnet is very much small when compared to the distance between center of magnet to the point of observation. Then I can write the above equation as B axial is equal to mu 0 by 4 pi into 2m R divided by, since L is very small, this term can be neglected, we can write R raised to 4, which is equal to mu 0 by 4 pi into 2m by R cube, and the direction of the resulting field will be along NP. We know that along NP means from north pole to the point P. We also know that the direction of magnetic moment is from where? From south pole to north pole, which means in our case field at point P and magnetic dipole moment are having the same direction. Right. Field at axial point P is and magnetic dipole moment has the same direction. Okay. Next, we are going to find out what is the magnetic field along the equatorial point of a bar magnet. Magnetic field along the equatorial point of a bar magnet. So imagine this is my bar magnet. Okay, and O is the center of my bar magnet. I am going to find out what is the effect at point P along the equatorial axis. Now, point P is at a distance R from the bar magnet. Okay, and distance between from center of the magnet to S, south pole is L. Similarly, distance from center of the magnet to north pole is also L. Why? Because total length is 2L. Now, if I want to find the field, what must I do? I have to keep a unit north pole at point P and find out what is the direction of resultant force due to the north pole and south pole of my bar magnet. For that, I am going to keep a unit north pole here, and see, north pole and north pole will repel, so direction of force will be pointing outward. I will call it as Fn. Similarly, south pole and north pole. So, unit north pole placed here. So, south pole and north pole, they will be attracting towards each other. So, direction of force will be like this. We will call it as Fs. So, what happens? These two are the sides of a parallelogram. So, the resultant will be what? The resultant will be the diagonal of the parallelogram. So, the resultant force will be acting in this direction F. Now, this angle is theta, so this angle is also theta, and this angle is also theta. So, what I am going to do? I am going to resolve my resultant force into two components, that is the horizontal component along this direction and the vertical components. Now, if this angle is theta, then definitely this component will be Fn sin theta, and if this angle is theta, this component will be Fs sin theta. Similarly, if this angle is theta, then component along the force will be Fn cos theta, and component of Fs along the resultant force will be Fs cos theta. Okay, so I am going to draw the vector diagram here separately. This is Fn, this is Fs, this is the resultant force F, this angle theta. What I am going to do, I am going to resolve Fs and Fn along the vertical direction and along the horizontal direction. Along the vertical direction, the component of Fn will be Fn sin theta and component of Fs will be Fs sin theta. Whereas along the horizontal horizontal direction, the component of Fn will be Fn cos theta and the component of Fs will be Fs sin theta. Now, if you look into this diagram, we can see Fn sin theta and Fs sin theta, magnitude wise, we are going to find magnitude wise both will be equal, but direction wise they are opposite, which means the resultant will be equal to 0 for the sin theta or the vertical component, whereas the horizontal component Fn cos theta and Fs sin theta will get added up. So, next we are going to write what is the magnitude of Fn and what is the magnitude of Fs. Force acting on point P due to North Pole is what Fn is equal to mu 0 by 4 pi Qm divided by distance between N and P. Now, what is the distance between N and P? See, this distance is R, this one is L. Then according to Pythagoras theorem, hypotenuse will be equal to R square plus L square the whole raised to 1 by 2. This side also R square plus L square the whole raised to 1 by 2. So, our equation becomes Fn is equal to mu 0 by 4 pi Qm divided by R square plus L square raised to 1 by 2 the whole square, which is 1. And what is the direction? Direction is from north to N to P. So, along the direction NP. Similarly, force acting at point P due to South Pole. Acting on point P due to South Pole is Fs is equal to mu 0 by 4 pi Qm divided by R square plus L square. What is the direction? Direction is from P to S, so along the direction PS. This is why I told magnitude wise Fn and Fs are same. That is why the vertical components which are acting along opposite direction gets cancelled. So, the resultant force at point P is F is equal to Fn cos theta plus Fs sin theta. Now, Fs cos theta. Now, since magnitude of Fn and Fs are the same, we can write it as 2 Fn cos theta, which is equal to what? Which is equal to the magnetic field along the equatorial point. So, we know the value of Fn. Next, we are going to find out what is cos theta. So, if we take this right triangle, this is theta, then cos theta will be equal to what? Adjacent side, that is length, divided by the hypotenuse, which is R square plus L square the whole raised to 1 by 2. Therefore, we get V axial is equal to 2 into what is the value of Fn? Mu 0 by 4 pi Qm divided by R square plus L square into what is the value of cos theta? L divided by R square plus L square the whole raised to 1 by 2. Now, on solving this equation, we get B equatorial. We get B equatorial is equal to mu 0 by 4 pi qm into 2l divided by r square plus l square the whole raised to 1 into r square plus l square the whole raised to 1 by 2 becomes r square plus l square the whole raised to 3 by 2. And what is qm into 2l? It is the magnetic dipole moment. So this can be written as B equatorial is equal to 0 by 4 pi m divided by r square plus l square the whole raised to 3 by 2. Now if my point P lies very far away from the magnet, then I can write R is very much greater than L. So the above equation becomes B equatorial is equal to mu 0 by 4 pi m divided by R cube. And what is the direction of the resultant force? Direction of resultant force is from P to this side. So I am going to write this point as R. So direction of resultant force is from P to R, and this direction is opposite to the direction of magnetic dipole moment, which is from S to P. So mu 0 by 4 pi m divided by R cube along the direction P R, and we can say direction of magnetic field along the equatorial point of the bar magnet is opposite to the magnetic dipole moment. Also, if you are comparing the value of B equatorial with the value of B axial, what is B axial? B axial is mu 0 by 4 pi 2m divided by r cube. We can say B axial is actually twice the value of B equatorial. Thank you.